Welcome to another class of process heat transfer. In this lecture I will talk about the topic that is known as the condensation heat transfer. Condensation occurs when the temperature of vapor is reduced below its saturation temperature, which is called Tsat. This is usually done by bringing the vapors into contact with a solid surface whose temperature, which is represented by Ts, is below the saturation temperature Ts of the vapors. But the condensation can also occur on the free surface of a liquid or even in a gas when the temperature of a liquid or the gas to which the vapor is exposed is less than the saturation temperature. So the liquid droplets is actually suspended in the gas. This will actually make the fog. So there are two distinct forms of condensations are being observed. The one is known as the film condensation, as you can see in this diagram, and the second one is known as the dropwise condensation. So first of all, let us take an example or try to understand the film condensation. So in the film condensation process, the condensate wets the surface and forms a liquid film on the surface that actually slides down, as you can see here, under the influence of the gravity force. The thickness of the liquid film increases in the direction of the flow as the more and more vapor condenses on the film. Here the thickness is very small of the film, of condensate film, and here the thickness is very high. And this is how the condensation normally occurs in practice. On the other hand, there is a second classification of the condensation, which is known as the dropwise condensation process. The condensed vapors forms the droplets on the surface instead of a continuous film, as you can see in this diagram, the different sizes of the droplets. And the surface is covered by the countless droplets of varying diameters. So as a result, the heat transfer rates that are more than 10 times larger than with the film condensation can be achieved. So the preferable condensation phenomena is the dropwise condensation. So in case of the film condensation, the liquid film which is present on the surface is blanketed by the liquid film, and this liquid film actually act as a resistance to the heat transfer. So that is why the film condensation process is not preferred and the dropwise condensation process is preferred. So this is a typical example of the film condensation. We now consider a film condensation on a vertical plate. This is called a vertical plate, as you can see in this diagram. The liquid film starts forming at the top of the plate and flows down under the action of gravity force. The thickness of the film, which is represented by this delta, increases in the direction of x, which is because of the continuous condensation at the liquid vapor interface. Here the thickness is small and there is a continuous process of condensation of vapors into liquids. So here the thickness is very high. So at the start of the condensation, or at the start of the origin, the thickness is small, and at the very far from the origin, the thickness of this film condensation is very high. So consider this gray color is the vapors and this pink color is the liquid, and this is the vapor liquid interface, and the mass of the film is moving in the x direction, right? So this is a kind of the velocity profile, and the liquid, which is the liquid layer which is adjacent to this solid plate, has the zero velocity, and as we move away from the solid surface, the velocity of the film layers increases, and at the center, at this point, it will have the maximum velocity, right? And similarly, this is the surface temperature is Ts, which is the far less temperature, and the temperature of the vapor is very high. So because of this temperature difference, surface temperature is very less and temperature of the vapors are very high. So because of the temperature gradient, so this temperature profile will be developed, because this point shows that the highest temperature, if this is the reference line, from this you can say that from this reference line to this point the T surface temperature is small, and this is the saturation temperature at which the condensation process occurs, and this is the vapor's temperature. This is very high temperature compared to both these temperatures. So the heat is the amount which is called HFG is released during the condensation process and is transferred to the film to the plate surface. This HFG is called the latent heat of vaporization, and when the vapors condenses into the liquids, this is the amount of heat which is basically released. So the Ts must below the saturation temperature for the condensation process. This is one of the must condition. So the velocity and the temperature profiles are also given here. That the velocity, I have already said that there is the velocity 0 at this point because of the no slip condition, and the maximum velocity of the liquid layer will be at the vapor liquid interface. So the temperature of the condensate, that is the Ts, which is at the interface and decreases gradually. The condensate temperature decreases gradually when it moves towards the wall, and which is at the temperature of Ts. So this is the kind of the film condensation film phenomena, and these are two temperatures and the velocity profiles. Let's move ahead. That in case of the forced convection involving a single phase, the heat transfer in condensation also depends on whether the condensate flow is laminar or turbulent, and we have already studied about the laminar and the turbulent flows. Again, the criterion for the region is provided for whether it is a laminar flow or the turbulent flow. This will be determined by the famous formula or the famous number which is called the Reynolds number. Reynolds number tells us that whether the given flow is in laminar region or in turbulent region. So this is the basic formula. Let me just bring my pointer over here. This is the basic formula of the Reynolds number, right? Rho V D over mu, right? Rho is the density of the liquid and V is the average velocity of the condensate or the liquid at the lowest part of the flow, which is meter in per second, and this is known as the viscosity of the liquid kilogram per meter per second, and this is known as the hydraulic diameter or the characteristic length, okay, over which the condensate is flowing after converting from vapors into liquid. So if the shape of the material over which the condensate is flowing is different, so this dH value will be different, right? And this dH is actually the ratio of 4 times the surface area over perimeter, right? And it will be equal to 4 times the thickness of the condensate film, right? Here we have different kinds of geometries, that is the vertical plate, right, and the vertical cylinder and the horizontal cylinder. So in each if the geometry, there will be the different the perimeter and the different surface area, right? So ultimately for different geometries we can put the values over here and calculate the Reynolds number, right? So if we replace this dH is equal to 4 times AC over P, right, we can get this formula, right? We can get this formula. So after replacing dH in this formula, with this one, 4AC over P, P is the perimeter, we can get this formula, right? And if we replace this DH with this 4 times the thickness, we can have this formula. So either you can use this formula, or this formula. But what about the last one, right? So the last formula can be determined by this mass flow rate of the condensate as the lowest part. So if we multiply the density and the average velocity and the area, and as you can see in this formula, this AC rho L, the density of the liquid, and the average velocity can be replaced with the mass flow rate. So if we replace these 3 terms, that is AC, rho L and VL, will replace these 3 terms with the mass flow rate. So we can have this formula 4 m dot over perimeter into the viscosity of the liquid. So we can use either of these formulas for the determination of the Reynolds number. So that will tell us that whether the flow is in laminar or in turbulent region. So previously we have used the latent heat of vaporization, which is the heat released as a unit mass of vapors condenses, and it normally represents the heat transfer per unit mass of the condensate formed during the condensation process. However, the condensate is in actual condensation process is cooled below to further some average temperature between Ts and the Tsat. So the condensation in the real processes, which is actually occurring in between any temperature between the surface temperature and the saturation temperature. As you can see in the previous diagram over here, this is the saturation temperature, right? And this is the Ts temperature. So in the actual processes, the condensation is occurring in between any temperature between these 2 temperatures, right? In between these 2 temperatures. So it might be over here, it might be right over here. So in this case, we can say that if the condensation is occurring over here at this point, so it will release, let's say, some amount of heat, right? And if the condensation is occurring over here at this point, it will release even more amount of heat. If the condensation is occurring over here at this point, it will release more and more heat. So usually we consider that the condensation is occurring at this point, slightly below the saturation temperature, and if the amount of heat which is releasing at this point is known as the latent heat of vaporization. So sometimes in the real processes, the actual condensation is taking place at this temperature. So if in the actual process, if the condensation is taking place at this temperature, we can say that it will release more heat in the actual. So therefore the actual heat transfer will be larger. So if it will release more heat, so the heat transfer will be larger. So there will be the possibility which is given by over here in this slide, as you can see, the modified latent heat of vaporization, right? So this is the actual heat of vaporization. This is the modified heat of vaporization in the case where the condensation is taking place in between these 2 temperatures, saturation temperature or the surface temperature, right? So we have to use this formula, modified heat of vaporization, right? So if the vapors are saturated vapors, right? So we can use this formula to get the modified value of the latent heat of vaporization. So the second case is if the vapors are superheated vapors, right? What will happen when the superheated vapors will cool down? It will then convert it into saturated vapors, and then the saturated vapors will cool down to the liquid. So there is a 2-step phenomena if we have the superheated vapors, right? So in that case, so we will use this formula. We will use this formula for the determination of the modified latent heat of vaporization. So this is the formula that we can use when the vapors are saturated vapors, right? So we'll just convert it into the liquid, and we'll use this modified latent heat of vaporization. If the vapors are superheated vapors, so we have to use this this formula for the modified latent heat of vaporization. For the determination of the heat transfer, we have to use this formula, right? The rate of condensation is equal to either given by this formula or by this formula, right? This is the formula that I have already used in the previous example, that where the rate of vaporization is we have to determine the rate of vaporization. So the rate of heat transfer was given, and the latent heat of vaporization was also given in the previous example. So we had to determine the rate of vaporization. So we determined in the second step of the previous example. So here CPV is the heat capacity of the superheated vapors, like it is determined at a given temperature by taking the average of the temperature of the vapors and the saturated temperature. If we add these two values and divided by 2, we will get a particular value of temperature. Then we will have to determine this CPV, the heat capacity of the vapors. So if we take the value of m dot from this expression and put it over in this expression, right, so we will get this modified form of the Reynolds number, in which we have the value of the condensation heat transfer coefficient, or the rate of heat transfer. So this is the expression if we have the rate of heat transfer, or the coefficient condensation heat transfer coefficient is given, right, like H. If it is given, so we can use this modified expression for the Reynolds law. If the rate of heat transfer, the rate of vaporization is not given, right, so we can use this formula for the determination of the Reynolds number. So the properties of the fluid, so there is the liquid film, right? So this is the liquid film, right? It is small over here, thickness is small over here, and thickness is very high over here. So the liquid fluid properties should be determined at one given temperature, right? So what temperature should we use to get the liquid properties? So we have two temperatures, Ts and Tsat. We'll take the average of these two temperatures, Ts and Tsat, and divided by 2, just like over here, and we have to determine the liquid properties of the condensate film at this TF, which is the average of Tsat and surface temperature. And we always know that the latent heat of vaporization should be evaluated at the given saturated temperature. Now let's have a look on the flow regimes, that the Reynolds number for the condensation on the outer surface of the vertical plates or the tubes increases in the flow direction. As you can see in this diagram, that here at the start the Reynolds number is very small and it goes on increasing and increasing, and at the end in the turbulent region it goes very high. This increase in the Reynolds number in the flow direction is due to the increase in the liquid film thickness, that is represented by delta. The flow of liquid film exhibits different regimes depending upon the value of the Reynolds number, and it is observed that the outer surface of the liquid film remains smooth. This is the outer surface, right, and the wave free for about the Reynolds number around less than 3. If the Reynolds number is less than 3, there is the smooth or the streamline flow over here, right, as you can see in this diagram. So the ripples or the waves may appear on the free surface of the condensate as the Reynolds number increases. If the Reynolds number is in between this 30 to 1800, you may see the waves or the wavy behavior on the condensate film, right, on the outside of the plate. So this region is known as the laminar wavy region, and where the maximum turbulence you can see and observe over here are there. So this is called the turbulent region, and the Reynolds number usually will be very high and higher than the 1800. The value of the Reynolds number would be higher than the 1800. So we can say that this region would be known as the turbulent region. So this is the basic formula that we have already derived in the previous slide. So from this formula of the Reynolds number, we can easily determine whether the flow is in laminar regime or the wavy regime or in turbulent regime. So the next is the heat transfer correlations for the film condensation. So we have different geometries. So we will determine the heat transfer coefficients for different geometries. So here one derivation is given, and I'm not going into the details of how to derive that particular formula, but for the vertical plates, in order to determine the heat transfer coefficient, convective heat transfer coefficient, you can have this formula, that the average heat transfer coefficient for the laminar film condensation over a vertical plate of a height L is given by this formula, right? And this is for the laminar film, so that's why the Reynolds number is in between 0 to 30. Here, this is the description of this formula over here. No need to memorize this formula, but if you get this in the numerical problem, you will be given this formula, or you will be asked to bring it in the formula sheet. So here the most important thing is this modified latent heat of vaporization. I have already explained the importance of this modified latent heat of vaporization in the previous slide. So this is again this formula that has been developed during the derivation. So this is the formula for the Reynolds number, and the modified form of the heat transfer coefficient in terms of the Reynolds number is given over here, for which if we say that the density of the vapor is far less than the density of the liquid, and the Reynolds number is in between 0 to 30. And for this formula, to determine the liquid properties, I have already explained in the previous slide that determine all the properties of the liquid at the average temperature, or by taking the surface temperature and the saturated temperature. So the values of the latent heat of vaporization and the density of the vapors must be determined at the saturation temperature. So this smaller section will actually explains that this is the unit consistent. So there are multiple terminologies over here. By putting all the units and after simplifying that, we will have the unit of watt per meter square per Kelvin, right? So it is the unit of convective heat transfer coefficient. So for the second geometry, first we have determined the convective heat transfer coefficient on the vertical plate in the laminar region. Second, we have the wavy laminar region, that in which the Reynolds number is in between 30 to 1800, right? So this is the derivation. This is the final formula where the density of the vapors is far less than the density of the liquid. You can use this formula. An alternate relationship in which the convective heat transfer coefficient for the vertical plate in the wavy laminar region in terms of Reynolds number is given by this formula, and the Reynolds number is ultimately connected with the modified latent heat of vaporization, and you can use this formula for the determination of the Reynolds number in case of the vertical plates in the wavy laminar flow, where keep in mind that the density of the vapors is far less than the density of the liquids. So for the third region, which is known as the turbulent flow on the vertical plates, so here is the formula that can be used to determine the convective heat transfer coefficient, provided that the Reynolds number is higher than the 1800 value, right? So I have already explained in most of the previous slides that the liquid film properties, the physical properties of the condensate or the liquid film properties must be determined at the average temperature of the film, and the average temperature of the film is determined by taking the average of the T saturation temperature and the surface temperature, right? So the value of the Reynolds number can be calculated in this case by using this formula, right? Or you can get the value of the convective heat transfer coefficient for the turbulent region or the wavy laminar region and the laminar wave-free laminar region by using this graph, right? So first you have the value, particular value of the Reynolds number, right? If it is less than 30, you are here. If it is in between 30 to 1800, you are in the wavy region, right? And it is, if it is above the value of the Reynolds number, so you are in the turbulent region, right? If you are over here, let's suppose over here at 100, you are in the wavy laminar region. You can just put the value and you can get the value of the convective heat transfer coefficient from this formula. And if you are in the turbulent region, let's say at 10,000 value, right? So you have different curves for the Prandtl number as well. So you have to determine the Prandtl number as well, whether you have to take 1, 2, 3 or 4 or 5. Let's say if you have to determine the value of the Prandtl number value 5, so given value of the Reynolds number is 10,000, you will take the vertical line up until this point and then draw the horizontal line over here to this axis. You will get the value of the convective heat transfer coefficient for the turbulent flow on vertical plates. So here is the different geometries. First, we have developed 3 different expressions for the vertical plate in which laminar, wavy laminar and the turbulent regions or turbulent flows occur. So here we are changing the different kinds of geometries. First we had vertical plates, now we are considering the inclined plates. So this is the inclined plate, right, and these are the vapors, and vapors are condensating on this inclined plate, and there is certain angle over here which is called theta, right? And this expression was developed over here and for the inclined plate. And for the inclined plate, first of all we have to determine the value of the H inclined by putting the value of this angle cos theta. So you will use the similar formula that is given over here above for the vertical plate in the laminar region. You can use the same formula, right, to determine the convective heat transfer coefficient for the vertical, and then to determine for the inclined plates you have to put the value of the H vertical, that is the convective heat transfer coefficient for the vertical plate in this formula in order to get the values for the inclined plates. So this formula just incorporating the inclinedness of this plate at a certain angle, right? So after putting the value in this formula, you can get the value of the convective heat transfer coefficient which is inclined at an angle theta. It could be anything. It could be any value of the theta. For the vertical plates or vertical tubes, you can also use to calculate the average heat transfer coefficient for the laminar film condensation on the outer surfaces of the vertical tube, provided that the tube diameter is large relative to the thickness of the liquid film. Now let's discuss about the determination of convective heat transfer coefficient for the horizontal tubes and spheres. So the average heat transfer coefficient for the film condensation on the outside or the outer surfaces of a horizontal tube is given by this relationship. So for the sphere, this is the expression for the horizontal tube. So this is a constant over here, right, 0.729. If you are using the sphere, you have to replace this constant 0.729 with the 0.815. So this is the expression for the determination of heat transfer coefficient, average heat transfer coefficient for film condensation on a particular horizontal tube. So let's take the comparison of the heat transfer coefficient relationship for the vertical tube of a height L and a horizontal tube of a diameter D. So we'll take a comparison, right? So we'll take the comparison of these two heat transfer coefficient of a vertical tube with a length L and a horizontal tube of a diameter D. So ultimately, if we compare these two, so we will come up with this expression, right? So in this expression, if we put H vertical is equal to H horizontal, so this ratio will be equal to 1, right? If we put H vertical is equal to H horizontal, so this expression on the left hand side will be equal to 1, and after simplifying this whole expression we will have L is equal to 2.77 into D. What does this mean? This means that for a tube, so we have said that for tubes we have said that vertical tube we have said that the height is L. For the horizontal tube we have said that the diameter is D. So ultimately, after solving this expression, we have said that the length of the vertical tube is equal to 2.77 times of the diameter of the horizontal tube. What will happen? So let's have a look on this description. This is very important because ultimately you have to design the heat exchanger, and it will help you a lot. For a tube whose length is 2.77 times its diameter, the average heat transfer coefficient of the laminar film condensation will be the same whether the tube is positioned vertically or horizontally. So this is the expression which says that the heat transfer coefficient will be the same if this condition is actually emitting over there, like length of the vertical tube is equal to 2.77 times the diameter of the horizontal tube. Then the laminar film condensation, the heat transfer coefficient will be same. Now what will happen that usually the lengths are the tubes are very lengthy, so length should be very high. So this is the case when the length is greater than 2.77 times the diameter of the horizontal tube, then the heat transfer coefficient is higher in the horizontal position. So from this data we have said that considering the length of a tube in any practical position application is several times its diameter, and we know that the tubes are very lengthy compared to its diameter. So it is a common practice to place the tubes in the condenser horizontally to maximize the heat transfer rate or maximize the condensation heat transfer coefficient on the outer surfaces of the tubes. So this is a very important slide in order to understand that in most of the condensers, so we place the tubes on the horizontal basis, like horizontally. So why we put the tubes horizontally? Because of on the horizontal tubes, the lengthy the tube, the higher will be the heat transfer coefficient. So the next is if we have the tube banks. Tube banks means if we have the multiple tubes which are placed with a certain distance over each other. This is the first tube, second tube, third tube and the fourth tube, and the condensation is taking place from top to bottom, and the liquid film is flowing from the upper tube to the lower tube and then so on, right? So what is going to happen that the average thickness of the liquid film at the lower tube is much larger as a result of the condensate falling on top of them from the tubes directly above. So on this tube the liquid is falling from here, on this tube the liquid is falling from here and then it comes here, and on this tube the liquid is coming all the way from this tube, this tube, this tube, and then falls over here. So what will happen, so the thickness of the condensate film on this tube must be very high, right? So if the thickness of this condensate film on this tube is very high, so what will happen, the heat transfer coefficient at the lower tubes will be much smaller because of the very high thickness of the tube. But assuming that the condensate from the tubes above to ones below drains smoothly, and the average film condensation heat transfer coefficient for all the tubes in the vertical tier can be expressed as, so we just assume that the liquid film is falling smoothly, so the thickness of the condensate film on the lower tube will not increase and it remains the same, right? So considering that the liquid is flowing smoothly over each tube, right? So for that case we have to determine the heat transfer coefficient. We can use this formula, right? And for different number of tubes we can just put this formula, right, H horizontal in this formula, which is 1 over n to the power 1 over 4 h horizontal. H horizontal can be determined from this formula, and after putting this one, and if you know the number of tubes, if the number of tubes are 5, so here n you can put 5, right? So you can determine the convective heat transfer coefficient for 5 tubes. If the tubes which are placed above over each other, if the tubes are 100, you can put the value of 100 and put the value of the horizontal convective heat transfer coefficient over here. You will get the value for that particular number of tubes and the horizontal heat transfer coefficient. So this relationship does not account the increase in the heat transfer due to the ripple formation and the turbulence caused during drainage, and generally yields the conservative result. So this expression is does not consider the presence of the ripples effect on the tube in the thickness of or in the film of this condensate. So it is not considering the effect of turbulence which is basically caused during the drainage process. So this expression does not consider these two effects. So for considering these two effects, we have to use another heat transfer coefficient expression which is beyond the scope of this lecture. So here is an interesting topic, that the effect of vapor velocity. In the analysis that we have in the previous slide, we assume that the vapor velocity is very small, and thus the vapor drag which is exerted on the liquid film is negligible, and which is usually the case that we have seen in the previous slides. That however, in most of the cases, the vapor velocity is very high. The vapor will pull the liquid at the vapor liquid interface along, since the vapor velocity at the interface must drop to the value of the liquid velocity, right? If the vapor velocity is very high, and if it comes in contact with the liquid, ultimately the vapor velocity will falls down and will be equal to the liquid velocity. So let's have a look on if the liquid and the vapors are moving in same direction or in the opposite direction, right? So if the vapor flows downward, that in the same direction as the liquid is moving, this additional force will increase. This additional force is the drag force, which is the vapors are applying on the liquid film, will increase the average velocity of the liquid and thus decrease the film thickness. So the decrease the film thickness will decrease the thermal resistance of the liquid film, and ultimately it will increase the heat transfer in that particular case. So if we say that the vapors are moving upward, right? So the upward flow, vapor flow has the opposite effects. The vapor which are moving upward and the liquid film is moving downward. So vapor exerts a force on the liquid in the opposite direction. So ultimately it will thickens the liquid film. If the liquid film thickens, so it will increase the thermal resistance, or ultimately it will lead to the decrement of the heat transfer. Let's have a look on the presence of the non-condensable gases in the condenser. So condenser, the purpose of the condenser is to condense the vapors into the condensate, right? So if there are non-condensable gases, like the white dots are the non-condensable gases, and the pink dots are the vapors which has to condense on this liquid film, right? This is a cold surface, right? So experimental studies shows that if there are the presence of the non-condensable gases in the vapor, which has the detrimental effect on the condensation heat transfer, right? So even a small amount of the condensable gas in the vapor, which caused a significant drop in the heat transfer coefficient during the condensation. So in the common practice that we have to remove these non-condensable gases from the condenser, so that the liquid in the condenser can easily condense down to the liquid. So it is a common practice to periodically vent off or to remove the non-condensable gases that accumulates in the condenser to ensure the proper operation, which means that if we remove these non-condensable gases from the vapor from the condenser, so the condensation phenomena of these pink vapors into the liquid will be easier. So the heat transfer in the presence of the non-condensable gas strongly depends upon two things. The number one, the nature of the vapors flow and the flow velocity, right? So the heat transfer in this case in the condenser where the non-condensable gases are present depends upon two things: the nature of the vapor flow and the vapor flow velocity. So a high flow velocity is more likely to remove the stagnant non-condensable gas from the vicinity of the surface, and which ultimately improves the heat transfer rate. Now let's discuss about the film condensation inside the horizontal tubes. So there are some cases in which we have observed that the combined flow of the vapors as well as the liquid inside the tubes. So it depends on the vapor velocities. If the vapor velocity is very high, so there is the probability that the vapors will make a flow channel in between the tube and the liquid will flow along the sides. So if the vapors are have very low velocities, so the vapors will move on the upper side, and the liquid will move on the lower side, whereas very small film on the liquid on the upper side of the tube wall. And most of the condensation process is encountered in the refrigeration, and in the air conditioning application involves the condensation on the inner surfaces of either vertical tubes or the horizontal tubes. So the heat transfer analysis of the condensation inside the tube is complicated by the fact that it's strongly influenced by the two things, that is the vapor velocity and the rate of liquid accumulation on the walls. So for the very low vapor velocities, we have a particular expression over here to determine the heat transfer coefficient for the fluid inside the tube. So this is the expression which can be used for the determination of the heat transfer coefficient. And for the Reynolds number, we have a general expression rho Vd and over viscosity when the Reynolds number is less than 35,000. Here the Reynolds number is for the vapors to be evaluated at the tube inlet condition using the internal diameter as the characteristic length. Here this d is the characteristic length, and it can be taken as the internal tube diameter at the inlet of the tubes. So the last topic of this lecture is the dropwise condensation, and it is very interesting that the dropwise condensation actually characterized by the countless or the numerous droplets of varying diameters on the condensing surface instead of making a continuous liquid film, and extremely large heat transfer coefficients can be achieved with this mechanism. In this diagram, as you can see, that this is a round shaped condensing surface on which the vapors are condensing. So there are very hundreds of tiny droplets which are on this surface, and there are some bigger size droplets which are on this surface. So the small droplets that actually combines or that form due to the nucleation at the nucleation sites on the surface, and they will ultimately enlarge or grow up as a result of continuous condensation process which is taking place at the surface. So they will ultimately emerge up as the bigger droplets, and these bigger droplets are basically slides down when they reach at a particular size. And you have actually observed this kind of phenomena when you place soft drink, chilled soft drink in the room, and you will ultimately see some kind of dropwise condensation outside the bottle of the soft drink. So ultimately only those droplets will fall down which will become in bigger size, and they will ultimately slides down because of the effect of the gravity force. So ultimately they will ultimately clearing the surface and exposing it to the vapors further. There is no liquid film in this case to resist the heat transfer. So in this case the two droplets are moving down. This is the first one and this is the second one, and they are big enough in size that they will ultimately flow down under the gravity force. As a result, with the dropwise condensation, the heat transfer coefficients can be achieved that are more than 10 times larger than those associated with the film condensation. But there is one issue, that the challenge is the dropwise condensation is not to achieve it, but rather to sustain it for the prolonged period of time. So this is a short-lived condensation process, that initially there might be the dropwise condensation, but later on it might be changed into the film condensation process. This is the expression that if the saturation temperature is 100 and you are at the temperature 22 degrees centigrade, you can use this expression by putting the value of Tsat. So if the Tsat is greater than 100, so you can use or take the value of the convective heat transfer coefficient in this dropwise condensation, that is 255, 3, 110. From this topic, this is all about this lecture, but let me add you one example related to the condensation process. So let us take an example, that the condensation of a steam on horizontal tubes. So the condenser, let me just read the question statement, that the condenser of a steam power plant operates at a pressure of 7.38 kilopascal. The steam at this pressure condenses on the outer surfaces of the horizontal pipes through which the cooling water circulates. The outer diameter of the pipes is 3 centimeter and the outer surfaces of the pipes are maintained at the temperature of 30 degrees centigrade. Determine the rate of heat transfer to the cooling water circulating in the pipes, and the second is the rate of condensation of steam per unit length of a horizontal tube. This is tube, that particular tube in which the cooling water is moving, and the outer temperature of this tube is maintained at 30 degrees centigrade and the steam temperature is 40 degrees centigrade. So you can determine the steam temperature by using the value of pressure, right? So from the steam table you can get the value of the temperature, right? It is given in this question statement. If it is not given, you can get the value of the temperature of the steam if the pressure is given from the steam table. Let me just go through this the solution, that the saturated steam of a pressure that is 7.38 kilopascal condenses on a horizontal tube at 30 degrees centigrade. Determine the rate of heat transfer and the condensation are to be determined. So for the assumptions, we'll take that the steady operating conditions exist and the tube is isothermal, right? So the properties of the water at the saturation temperature of 40 degrees centigrade corresponding to this 7.38 kilopascal, that it is given in the question statement. At this saturation pressure, the temperature of the steam is 40 degrees centigrade. If it is not given, like, you can get it from the steam table. If the temperature is given, you can get the value of this pressure from the steam table, or if the pressure is given, you can get the value of the temperature. So the enthalpy of vaporization at this temperature or pressure is given by here, and the density of the vapors are also given here. So in most of the time I have said that the liquid properties must be determined at the average temperature of the saturated temperature and the surface temperature. So the saturated temperature is 40 degrees centigrade and the surface temperature is 30 degrees centigrade, and if you take the average, and it will become 35 degrees centigrade. So you have to determine the liquid properties. So what are the liquid properties? So the density of the liquid and the viscosity of the liquid, the heat capacity of the liquid, and the thermal conductivity of the liquid, right? So it is given in, you can take it from the table which is given in the book, or you can take it in the appendix from the book which is being used for this course. So So we have to determine first the modified latent heat of vaporization. I have already explained that the reason why we determine the modified latent heat of vaporization. That so if the temperature at which the condensation is taking place is in between this temperature, that is the saturation temperature, and the surface temperature, so we have to use this modified latent heat of vaporization. So if we use the modified latent heat of vaporization, we will ultimately come up with the actual value of the heat transfer or the convective heat transfer, right? After putting all the values and simplifying that, you will get the modified value of the latent heat of vaporization, which is equal to 2435 into 10 raised to the power 3 joule per kg. So we have most of the time said that the density of the vapors is far less than the density of the liquid, which is here over the density of the vapor is 0.05 and the density of the liquid is 994. So there is a huge difference. So the rate of the heat transfer coefficient for the condensation on a single horizontal tube can be determined by this expression 1031, and which is given over here, and I have also mentioned in the lecture slides. So everything is almost given, that the value of the gravitational constant and the density of the liquid and the density of the vapors, modified latent heat of vaporization, thermal conductivity, and the diameter, viscosity, saturation temperature, surface temperature, each and everything is given. So after putting the values in this formula, so you can get the value of the convective heat transfer coefficient, which is 9292 watt per meter square per degree centigrade. So the next is to determine the rate of heat transfer. So for the rate of heat transfer, we need to determine the area of the tube. So the area can be determined by dl, the surface area of the tube, after putting the values per unit length. So per unit length is 1 meter, right? It is mentioned in the question statement, right? The diameter is given, right? But per unit length is also given. Unit means 1 meter length. So after putting the value, so we have the area, and this is the simplest formula of the Newton's law of cooling, that after putting the values, you can get the value of the heat transfer rate during the condensation process, and which will be equal to 8758 watts. So for the determination of the rate of condensation of steam, we have the famous formula that I have also used this formula in the previous example of the same lecture. So this is the rate of condensation of the steam, and this is the modified latent heat of vaporization, and this is the heat transfer rate that we have determined in the previous slide, So after putting the values and simplifying that, the value of the rate of condensation of the steam will become equal to 0.00360 kilogram per second. And if you convert this kilogram into second, you have to multiply it with the 1000. So it will become 3.6 gram per second. So the final statement is, therefore the steam will condense on the horizontal tube at the rate of 3.6 gram per second, or 12.9 kilogram per hour per meter of its length. With this, this lecture is over.